Alright, so recall that in the last class we had learnt what is A, adjoint of A, which are nothing but the transpose of the cofactor matrix, and in a hurry I just showed that A into adjoint of A is determinant of A into I, and from there we got the inverse. Alright. So what I would like now to do is that proceed with that idea itself and do something so that there is a clarity of thought. Fine. So I take the same example. Alright. So let's look at the example that we had taken. We had A, which was 1, 2, 3, 2, 3, 1 and 1, 2, 4. We had computed the adjoint of the matrix. I did it in a hurry, so we will do it again in some sense, but for a different matrix. And then I want to compute what is x times identity minus A. So x times identity is this matrix and minus A is it is. So this is nothing but this matrix is equal to x minus 1, minus 2, minus 3, minus 2, x minus 3, minus 1, minus 1, minus 2, x minus 4. I want to compute the adjoint of this matrix. What is adjoint of this matrix? Adjoint of xi minus A is nothing but the first entry is this. So adjoint is going to be determinant of this matrix. So I have this determinant of this matrix, which is x minus 3, minus 1, minus 2, x minus 4. Fine. Then I have to compute the adjoint of this. Alright, this entry, a corresponding entry. So if I have to look at this entry, it is minus 2, minus 1, but I have to put it as, so I am looking at this part, so I have to put it as a column here because it is a transpose, cofactor transpose. So I have to put it as minus 2, minus 1, fine, and then it is minus 1, x minus 4 here, fine. Similarly, for this I have to look at minus 2, minus 1 and x minus 3, minus 2. Now the next one I have to look at this part. So this part gives me remove this and remove this. So it is minus 2, minus 3, minus 2, minus 3, minus 2, x minus 4. Then the diagonal, remove this, x minus 1, minus 3, minus 1, x minus 4. I hope I am not doing a mistake. Fine. This into this, so x minus 1, minus 2, minus 1, minus 2. When I do the calculation, I will know the mistakes. Remove this, so it is minus 2, minus 3, x minus 3, minus 1. Then this and this, so it is x minus 1, minus 3, this and this, so it is minus 2, minus 1. Here it is this and this, so it is x minus 1, minus 2, minus 2, x minus 3. So this I would like you to see that this is nothing but x square minus 7x and then plus 12 minus 2 is plus 10. Alright, I hope it is correct, plus 10, fine, and so on, fine. What is this entry? This entry is minus 2x. Alright, so one thing I have forgotten, it is minus 1 to the power I plus j, so it was plus sign here, there will be minus sign here, plus sign here, minus, plus, minus, plus, minus, plus. Alright, because it is minus 1 to the power I plus j, that has to be taken care of. I did not take care of, therefore I was getting wrong signs. Alright. So as I said, I always do mistakes. So if I look at this part, it will give me minus of minus 2 times x minus 4 minus 1, which will be minus of minus 2x plus 8 minus 1, which is 2x minus 7. 2x minus 7, fine. If I look at this part, it is plus sign, so it is 4, minus minus plus, x minus 3, so it is x plus 1. Fine. So, I would like you to compute it yourself. So, this turns out to be equal to, let me complete it so that I use it afterwards, 7x plus 10, 2x minus 7, x plus 1, 2x minus 2, x square minus 5x plus 1, 2x, 3x minus 7, x plus 5 and x square minus 4x minus 1. Fine. So, this is the way I write it down. So, this is this. Now, what is important is I can go and write this also equal to, just see it nicely, it is x square, there is no x square here, there is no x square, so 0 0, 0 x square 0, 0 0 x square. Let us look at coefficient of x. So, coefficient of x comes from, or here I could have written as, let us see. So, coefficient of x comes from minus 7x, 2x, x, 2x, minus 5x, 2x, 3x, x, minus 4x, plus there is a constant which is 10, minus 7, 1, minus 2, 1, 0, minus 7, 5, minus 1. So, this is same as x square times identity plus x times a matrix which is minus 7, 2, 1, 2, minus 5, 2, 3, 1, minus 4 plus 10, minus 2, minus 7, minus 7, 1, 5, 1, 0, minus 1. I would like you to see that this matrix, just let us go back, this matrix is same as adjoint of A, 10, minus 7, 1, so you can say here. So, if you look at here, 10, minus 7, 1 is the constant, minus 2 is the constant, 1 is a constant, 0 is a constant here, minus 7, 5 and minus 1, all right. So, I would like you to see that I get here, this is as x square identity plus x times some matrix B, all right. I do not know what that matrix B, but there is some matrix plus adjoint of A. Is that okay? Now, let us multiply. So, this matrix with xi minus A. I want to multiply xi minus A with this matrix, x square I plus xb plus adjoint of. I want to multiply this. Fine. So, what we are doing here is we are looking at xi minus A. Now, what is this matrix? This matrix was adjoint itself. So, this was adjoint of xi minus A. So, with what we have learnt that A into adjoint of A is determinant of A into I. So, this will give me, it will be determinant of xi minus A into identity. Fine. So, we need to compute what is determinant of this and then do the calculations. Is that okay? Or you can just multiply it here and see what is happening to you. Fine. So, whatever the calculations. So, this turns out that, let me calculate the determinant directly now. Fine. So, let me compute the determinant of this matrix. So, determinant of this matrix is x minus 1 into x square minus 7x plus 10 that we looked at, then this plus 2 times minus 2 of this, fine. So, minus 2 plus 2, so minus 2x and minus minus plus 8, this minus 1 minus 3 times minus 4 plus x minus 3, I hope it is correct. So, this is same as x cube minus 7x square plus 10x minus x square plus 7x minus 10 minus 4x plus 14 minus 4 minus 3, I think this is wrong, I hope, minus 4, let me just look at, this is plus 4, then x minus 2, this is plus 4. So, it is x plus 1. So, x plus 1. So, minus 3x minus 3. So, this is nothing but x square cube minus 8x square. Let me check. 10 plus 7x minus 7x is 0. So, plus 10x, fine. And then it should be minus 1. So, let us see minus 10, minus 13 plus 1. So, it is plus 1. So, this is same as minus of determinant of A, all right, fine. So, I would like you to see that. So, this is equal to x cube minus 8x square plus 10x minus determinant of A whole times identity, fine. Now, what I would like you to see here is that this part, this is an identity in X, where the coefficients are matrices, all right. I have matrix I here, A here, identity B and A, adjoint of A is again a matrix. Here also I can think of this as a whole x cube times identity. So, the coefficient of x cube is identity, coefficient of 8x square is also minus I, coefficient of 10x is identity, and there is a constant term which is minus determinant of A. So, it is again an identity as far as matrix identity is concerned. Since it is an identity in matrix, I can replace. So, we can replace x by A itself, by A, all right. So, if I do that, then I see here that I am going to get A times this times A into something which will be 0 times something which will be 0, fine. So, the important thing here is that in this expression, since this is an identity in X and the coefficients are matrices, I am allowed to replace X by the matrix A, fine. And therefore, what I see is that this is the left hand side. What about the right hand side? The right hand side is A cube minus 8A square plus 10A minus determinant of A into identity. There is no change here because there is no x. So, this is equal to this. So, what we are trying to say from here is that A cube minus 8A square plus 10A minus determinant of A times identity is 0, fine. This part is called what are called the Cayley-Hamilton theorem. It says that, what the Cayley-Hamilton theorem says, that every matrix satisfies its own characteristic polynomial. So, in this example, all right, this is the characteristic polynomial. Or the same as determinant of xi minus a, all right. So, determinant of xi minus a is called the characteristic polynomial, and Cayley-Hamilton theorem says that every matrix satisfies its own characteristic polynomial. So, just replace x by a. So, a cube minus 8a square plus 10a minus determinant of a into identity is 0. This is what it says, all right. Now, the important thing to note here is that I cannot replace x in this expression. So, let us go back here. From where did I get? Here, all right. So, in this expression, if I look at this expression here, all right, cannot replace x by a. This is not allowed here because a minus 1 does not make sense. All right. So, to make sense of things from this, I had to go to adjoint of A, rewrite it as a matrix identity, rewrite it as this in terms of 3 matrices. All right. In general, if there are n, I will have to write n matrices and then do the multiplications and so on. Is that okay? So, from there we will get the ideas. Now, here just to spend some time, I would like you to understand that why did I get this expression, all right, because there also I did not explain you much. So, let me explain it here to you. So, how do I get that xi minus a or a into adjoint of a? Adjoint of a is determinant of a into I. How do I get this? So, let me try to make you understand this in this example here, all right. So, I had this matrix with me, this was A, this is adjoint of A. So, let us look at what exactly we are doing. When I am multiplying this matrix with this, so I am multiplying x minus 1 with this one. So, I will just write it down. So, I am multiplying x minus 1 to this, fine. That is minus 2 times this part, fine. So, just let us look at things A11, A12, A13, A21, A22, A23, A31, A32, A33. This is my A. Now, when I am looking at the adjoint, fine, what I have is C11 with a minus plus sign, fine. Then I have got C12 here with a minus sign, C13. Then I have C21 with a minus sign, C22, C23, C31, C32, C33. So, when I multiply it, the first part is summation. So, look at here this one, all right, 1 1 1 1 1 2 1 2 1 3 1 3. So, it is A1j C1j, j equal to 1 2 3, and minus sign is also coming into play again as usual. So, I do mistakes. So, there is no minus here, this is this, because this itself comes with a minus sign, all right. So, Cij itself comes with a minus sign, minus 1 to the power I plus j determinant of this, it itself comes, fine. So, there is no minus sign here. Now, this into this part, if I look at this into this, it will be here. So, it will be A11, 21, 12, 22, 13, 23. So, here it is A1j, but is not 1 but C2j, all right. Similarly, the last one will be A1j C3j, fine, C31, 32, 33. Now, question is why is this 0, why is this 0, all right. So, let us look at this what exactly we are doing. So, when I am looking at A11 C21 plus A12 C22 plus A13 C23, I have got the matrix A11 here, all right, fine, with a minus A12, I can put here minus here. So, or I can replace this by just A12, and then we will see what exactly we are doing. I have A13. Now, what is C21? C21 is nothing but minus 1 to the power 2 plus 1, determinant of remove the second row and remove the first column. Second row and first column I have to remove it. So, I am looking at A11, A13, this goes off and this goes off, sorry, 2 1. So, A12 and this, and then A32, A33. So, I have got here this. So, when I am computing the determinant, this I am not bothered about for the time being, minus sign, just look at this. When I am computing the determinant, this is supposed to appear here A12, A13, A32, A33. So, this into this part is going to be this, all right. So, what I am saying is this part is this one, fine. Now, I want to look at A12 into C22, there is a minus sign, let us not worry about the for the time being. A12 into C22, C22 is nothing but, C22 means remove this and remove this. So, A11, A31, A11, A31, A13 and A33. Fine. There is a plus sign here, minus 1 to the power 2 plus 2. So, there is a plus sign here. Fine. So, now understand the where does the minus and where does the plus come. Here I had a minus sign extra. Fine. Is that okay? In this I had a minus sign extra. Now, if I look at here, it is C22 has no sign, but when I want to multiply here, if I write here A11 and A31, it will minus A12 times this matrix, this matrix, this matrix, this matrix, all right. So, there is a minus which is coming into play. So, I could have done here, I could have put a minus sign here somewhere and then multiplied here minus, I could have multiplied minus here, fine, is that okay? And similarly, a minus here, not in this, but in C31 minus, and looked at the whole thing. So, what we see is that when I am computing this, basically I am looking at determinant of this matrix in which there are two rows are same, and therefore, the determinant is 0, all right. So, the same argument goes here, since I am looking at 3. So, again this part will get replaced by A21, A22, A23, but the first two rows will be the same, and so therefore, they will become 0 as such, fine. So, the last part today, all right, what is called the Cramer's rule, or I will just remind you of this theorem, and then so A n cross n, then the following statements are equivalent. One, A is invertible. 2, determinant of A is not 0. 3, the system Ax is equal to B has a unique solution for every B. All right. So, there are some more conditions, 5 more or 4 more, write them down and complete it, fine. Now, let us come to what is called Cramer's rule. So, what we are doing is we are going to look at solve the system Ax is equal to B, and then there is a formula which you need to look at. So, we write what is called the matrix A1 as, I have the matrix B here, fine. Look at the second column, looking at 1 here to second column, and so on till the last column. This is my matrix A1. Matrix A2 is, just write the first column, all right, then B here, then the third column, and so on till the last column, fine. So, the important thing is this is 1, so the first column is replaced by B. 2, so second column is replaced by B. So, in general, when I look at A n, it will be first column will remain till the last but 1. So, n minus 1 column will remain, B will come here, fine. So, it says that if determinant of A is not equal to 0, so we know that then x I is equal to determinant of A I upon determinant of A, fine, for 1 less than equal to I less than equal to n, and our x is x1, x2, xn transpose. Our vectors are always column vectors, therefore, I need to put a transpose here, fine. So, this is what the Cramer's rule says. Let us try to understand Cramer's rule now, fine. So, proof. Now, we have been given that determinant of A is not 0, implies A is invertible, implies the RREF of A is identity, implies RREF of A is identity, implies there exists an invertible matrix P such that PA is identity. Fine. So, what do you mean PA is identity? It means that, all right. So, I have got, so let us look at A1. I want to compute what is P times A1. P times A1 will be P times A1 is B, then the second column of A, third column of A, so on till the last column of A. So, we know what is P times A is identity. So, I am looking at P of A1. So, this is same as P times B, P times A of this, P times A of this, P times A of this. So, this is same as PB. What is this? This is supposed to be the second column of identity. This is the second column of identity, this is the third column of identity, and so on. This is the nth column of identity. So, therefore, determinant of P times A1 will be equal to, all right, look at the 1 1 entry of the first entry of PB. Is that okay? Fine. So, let us again understand what we are doing. So, I have P times A is identity. I am looking at the augmented matrix this. Fine. Apply P to it. What I get here is identity and P of B. Fine. Since there is an identity here, it means that x1 is nothing but the first entry of PB, x2 means second entry, xn is equal to the nth entry. Fine. Important. Again, understand that determinant of A is non-zero, implies RREF of A is identity. It means that there exists an invertible matrix P such that P of A is identity. So, just multiply P to the augmented matrix, I get I and PB, and what you know is that since there is an identity here, therefore, the system of equation has a unique solution given by x1 is equal to the first element of PB, x2 equal to the second element of PB, and so on. So, what I see here is that determinant of P of A1 is also same as first element of this. Is that okay? So, therefore, I get that determinant of P A1 is this, and therefore, x1 is nothing but this. Fine. So, what we know is that, so PB of 1 is equal to determinant of P of A1, which is same as determinant of P into determinant of A1 divided by 1, which is same as determinant of P into determinant of A1 divided by determinant of P times A, because I gives me determinant of identity, which is same as determinant of P into determinant of A1 divided by determinant of P into determinant of A. This part cancels out, you get this is equal to determinant of A1 upon determinant of A. Fine. The same idea you can use to prove that in general PB of j is equal to determinant of Pj, so determinant of Aj divided by determinant of A. Fine. The idea being same, the only thing is that since you are looking at the jth part here, all right, since you are looking at the jth part here, everything will remain same. The jth component here will become PB. Fine. And since the jth component is PB, the determinant of this matrix will be nothing but PB of j. Fine. Is that okay? So, when you look at P of Aj, determinant of that, it will turn out to be this, because everywhere else it is identity. Fine. And therefore, you will get this. So, I would like you to keep track of this. Mostly we are not going to use Cramer's rule, but you should know it. Fine. So, this finishes our chapter on system of linear equations, and in the next class what we will look at is what are called vectors, the general setup of vectors. What we had learnt was, recall that whenever we solve a system of equation, we have been able to solve it and then get some relationship between lines, planes, and so on. but there was a hidden relationship in vectors. So, we need to understand the vectors in a proper way, that is the first thing. Second is, solving a system of equation also resulted in trying to understand rows and columns, in the sense that it told us that determinant of A is not 0, means the columns are in certain sense giving me some information, rows are giving me some set of another set of informations. Can I relate those ideas, because they are basically looking at columns as vectors, you can also look at rows as vectors, fine, and then build upon those ideas. So, from next class onwards, we will not look at system of equations, but we will be using those ideas. System of equations ideas will be used again and again to get our results, to look at new ideas, new definitions and so on. All the things will be based on solving the system Ax is equal to b, unique solution, no solution and infinite number of solutions. They lead us to different ideas, what are called linear combination, linear span, fine, linear independence and dependence and so on. So, please read it before you come to the next class. Thank you.